The true false was they're all false. Did you know that? You did?
That's the first couple false moves like asked him.
Oh,
He always does that. Hey, Kyle, how's it going?
good. There you guys.
All right. Give me a second. I gotta get you set up. I just got here.
Sweet hat you got.
You see my hat, Kyle?
Yeah. Instantly makes you smarter.
It's my thinking cap. It's a thinking
Yeah,
cap.
your thinking cap. Nobody's gonna outsmart you wearing that hat.
That's right. I almost got you up here. That's great, by the way, last time. Good work. You hide your stupidity well.
I know. Like we said, it's better to be that way, though, right?
Absolutely. All right. Go. Luke right there in the front.
Yeah.
Pay attention. Make sure you're taking notes, Luke. All right, I think you're good, Kyle.
All right, let me get her fired up here.
Anybody want one?
No.
It was a gift from you guys. It's a gift from you guys.
I don't want to.
They're warm. They're warm.
That makes it worse.
Oh, yeah. That's even warmer that way.
The upper pocket.
You know, I like the back pocket, you know? Even warmer back there, you know? Snacks. You always have snacks with you.
Washing those pants is gonna be a nightmare.
Yeah. These don't melt though, you know? Good.
That sounds like from experience.
Yeah, it is from experience.
All right.
Does Tim? Fine.
You ready, Barry, or you want me
Yeah,
to
we're done,
wait
yeah.
on you? Okay. Just gonna quickly flip through the slides we went through, just to recalibrate us from Monday, right? So we talked about why we use post-tensioning on these buildings, all the benefits, the reduced seismic mass, the reduced height, the reduced cost of doing the skin on the exterior building, you know, easily saving $500,000 just an exterior skin on a taller building, being able to throw an additional few floors onto a building, the reduced foundations that you get with post-tensioning, the ability to do large transfer beams like what we saw in that picture, also the ability to do two-way slab transfer slabs that you would have for a podium structure like you see in the Bozeman region quite a bit. You good?
Yeah. I found a way to get your sound to go through the speakers.
Oh,
so.
perfect. All right. And then we just went through the basics of, you know, what the hell a tendon even looks like, how they're put together, the fact that they're not bonded, unlike what you guys have probably been studying so far with a traditional precast girder that would be bonded. And we would talk about the distributions you'd have, how the uniform banded distribution's kind of been the classic one that's been used for years and years. Now, we talked about beams and how, you know, there's a time and place to use post-tensioning in beams, such as a transfer girder, right? But then you don't want to use them in a tight beam where you have a bunch of congestion going on in there. At the very end, we were starting to get a little bit rushed, but we talked about sweeps. And, you know, just because it's curved up and down, it's going to be picking up the slab or pushing down. But if it's curved horizontally, you're also going to be inducing a horizontal force into your slab or your diaphragm. So if you have huge sweeps, it's something to try and consider both at the local level and the global level. Locally, not trying to let those tendons roll out of the slab or break into a opening that you might have, such as this one for a mechanical shaft. Globally, it's introducing on a big sweep, you're introducing a lot of kind of diaphragm type forces into your slab. So just something to kind of consider a little bit there. Then we had just started talking about, yeah,
The sweeps are just to avoid like mechanical and stuff like that, right? That's
yeah, to avoid mechanical. Also, your column lines usually they're not often straight; they'll zigzag. One of the benefits of doing a two-way slab is you don't need to have columns on grid; they can be kind of wherever on it. One of the first times that they ever did a banded uniform layout was on a building. It was the Watergate building, actually, in DC, where the column layout was not straight in any direction, but they were able to sweep the tendons with the banded set in a certain path and come up with a to follow the columns, and they were able to identify a load path from there. Then we haven't gotten into design yet. We're going to get deeper into this in future lectures, but there's really not that much rebar that goes into these post-tensioning slabs. You have to have a little bit to support the elevation of your tendons, but that's not doing anything structurally, right? It's just supporting the actual height of your tendon itself. And the other is, no matter what, you have to have some minimum amount of rebar over your column head. And we had discussed that that was really for crack control and for ductility within the slab itself. So when you look at the slab from a service level, it's a gross cross section. These slabs, if it's two-way slab, they have to remain uncracked. So adding rebar doesn't really help you with any of your service level calculations because it doesn't help you from that gross perspective on your stiffness, right? So where it does help you would be in strength, because now you have which we'll go into this further, but you're looking at crack cross section because you now have some reinforcing over your column head right there in addition to your PT tendons. However, when you look at usually strength level, your PT tendons are plenty of steel by themselves for your strength calcs, and you don't need that additional rebar. So that additional minimum amount of rebar that's required, and that's this ratio right here, this 0.0075 of your kind of gross cross section, that really just provides some ductility in the slab, an extreme negative flexure event, and some crack control. And remember, when you look at your negative moments over column head in FEA, you're going to get a big spike like this. The reality is that spike's probably going to be tapered out a little bit, but this line right here is most likely going to be locally greater than your rupture that you'd have. So it's going to be somewhat greater than 6 square root F prime C on there. And that steel helps provide, the steel we have in the left-right direction helps provide a little bit of crack control that you'd see from that spike in negative flexure right there. And then again, in a large lateral event, you got a little bit of ductility. You're not using that for your energy dissipation. So you're not using it as your ductility that you'd be using in your shear walls or your moment frames that you're actually counting on, detailing for that ductility. This is more just a feel-good, warm and fuzzy ductility. And this amount of steel was the steel they used in the original testing back in the 70s, and this is how it got codified and has been used ever since. And it's not going away anytime soon on there. Past that, the only steel that you'd have is in your tension regions. If you exceed a certain tension stress, 2 square root F prime C, you do have to put in a little bit of rebar. And that rebar is equivalent to twice the amount of tension you have in your cross section. You sometimes see that in M-bays, but it's very common to have a post-tension slab where the only rebar you actually have in that slab is over your column head, just how we see right there, right? Another slide we briefly touched at the end of the conversation on Monday, but this one's showing, you can see that negative flexure steel, the minimums we have to have. It's a corner column condition. So your PT tendons are at mid-height because they're always going to exit at mid-height. So you don't have that height that you want, that depth for flexure calcs, right? Because ideally you want your steel at the highest elevation possible. And your PT tendons are at, if it's an 8-inch thick slab, they're exiting at your CGS, which would be 4 inches right here. So sometimes this steel here can actually help you a little bit on those corner columns where you might need a little bit. But again, you don't have a lot of stiffness, so you don't have a lot of negative moment. Chances are your post-tension tendons are going to do just fine. We talked about these stud rails. It's probably a new concept for you guys, but these are what helps you with your shear cracking, right? So your punching shear is going to come at, in theory, about a 45-degree angle. Now, the pre-compression is going to flatten that angle a little bit, right? If you're to look at a stress block and you have a bunch of pre-compression on there, that's going to flatten your shear cracking angle on there. These are a very common way of helping to reinforce for punching shear, which often becomes, with such a thin slab, often becomes your controlling design criteria on there. So just pushing forward a little more to show you guys some more fundamentals of what these slabs look like. Sometimes you don't have access to stressing a post-tension tendon group. It might be because there's a building that's right up against it. It might be because there's a garage scissor ramp and you can't get in there. So you have to do these blockouts that are temporary. You block them out, you pour the slab, you stress the tendons, you cut the tails, then you come back and you pour this back in. So sometimes you have to get creative, and you'll see these, they're called stressing blockouts. And all they do is they allow you to stress the slab at a certain location. Another unique thing that you'll run into sometimes is, here's a project did years ago and it had a curved edge form to it. And our tendons are coming in, and if we were to use a regular pocket former, they'd be coming in askew. If you were to actually put them in askew, you run the chance of kinking that tendon and snapping it. So they make these 30, 60 degree pocket formers here and here that you can put in when you're doing a curved area, so you can still have stressing access while keeping your PT head perpendicular to the direction, parallel to the strand, but perpendicular to the direction that you're trying to put that pre-compression into on it. So shop drawings, you as the engineer, you're going to tell them your high point needs to be, let's say it's an 8-inch slab. You might say your high point needs to be 7 inches over the column head. Your low point needs to be 1 inch mid-span, and you need this many kicks of force on there. Then the supplier, who's actually supplying the post-tension tendons, they're going to do the actual friction loss calcs, even though you know what they're going to come up with roughly at the end, but they're going to do the very detailed calcs. And they're also going to lay out exactly where to put those tendons on there. So this is a very common look at what a shop drawing is going to look like. And the first thing is, you can see these tendons here, and it got cut off in the snip, but they have a certain spacing. And these are the uniform tendons right here between it. And that spacing, remember, that spacing can't exceed 5 feet or 8 times your slab thickness. And typically the 5-foot number controls on there, so, or 8T, right? And they're going to lay out those tendons. And if you have a weird layout of forces, it might not be 3 tendons every 5 feet. It might be 3 tendons and 4 tendons and 3 tendons and 4 tendons, or some pattern like that to get that exact force that you want on there. And how that's represented is it's represented with these symbols. So right here, you can see there's a triangle. That triangle represents 3 tendons, right? Then you can see the next line is 4, or it's a square representing 4 tendons right there. And then it's 4, 4, 4, 4, 4 all the way down. The other symbols you'll see a circle for 2, half circle for 1 on there, and every now and then you see a diamond that's 5, but 5's pretty uncommon. You usually only see in your banded tendon sets, not much with your uniforms on there. So they're going to lay that out, and then they're going to tell you what your theoretical elongation is going to be on those tendons. So when you go to stress it, they're going to say, when you stress it and you put on that 33,000 pounds, you should get 9 3/4 inches of deflection. And if you think about that, that's a lot of deflection that you're going to see. If you took a piece of steel and pulled it and you got 9 3/4 inches of deflection, that's quite a bit. But these things are, this particular tendon line is 122 feet long on there. And what they'll do is they'll tell you, all right, there's 43 tendons in here. You don't really care too much about that, because you as an engineer, you're just going to kind of look at the average within some sort of trib width and make sure they have the right pre-compression in there. They're 122 feet long. Now they're going to be an extra 3 feet of tail length. So that really means you're probably about 119 feet-ish of slab length on there. This little symbol right here, this means it's a dead end. So you're not stressing on this end, that little cross symbol right there. That's a dead end. Versus over here, see this arrow right there? That arrow means a live end. That's where you're going to be stressing from. It doesn't matter from an engineering standpoint which direction you stress from. You don't care about that. You leave that up to the guys out on the field, which way they want to do it. You're just checking to make sure that the tendon count is correct. And they got that part right, and they got the drapes right on there as you get these shop drawings for it. The other thing you'll see on these is you'll see copper and you'll see different colors painted on there. Those colors are when they manufacture these tendons at the factory, what they'll do is they'll spray paint the anchors a certain color so that they know when it's all bundled up, it gives them an easier ability to know which tendons go where. So these might be copper, you might go further down, it'll be blue, then they might have blue-green. So all that color means that's just a guide for the folks out in the field on there. Then what they'll do is, remember I said you're going to specify the chair height, or sorry, you're going to specify the high points and your low points, and that's it. They're going to actually go specify the curvature that you're going to get in the slab itself. So if you had a slab like this, right, and your tendon comes in mid-depth, goes down to a low point, and goes up to a high point over, we'll just say there's a column right there. We'll say this is the end of the column right there. Here's our PT head here. You're going to tell them exit at mid-depth, which will, that's always your center of gravity of your slab right there. You're going to give them the CGS, the center of gravity of your steel, the centroid of your steel for your low points and your high points on there. So if I'm calling out a 1-inch CGS on here, on my drawings, that's really saying I need the center of that steel to be 1 inch, but that doesn't necessarily correspond with the chair height. So when they do the chairs, what they'll typically do is they'll do a chair, it's a little plastic chair, and then it's got a number 4 bar right here, which we all know that's 1/2 inch in diameter, right? And then it's got your 5/8 inch tendon running right here. I just round that. I just pretend that's a 1/2 inch. So to the center right here from your chair height, I say that distance, in my quick math, I just say 3/4 inch. And so when I'm looking at their chair height, and that's what they're really calling out on these drawings, I add 3/4 inch to get to my CGS on there. So if I'm looking at, a 5-inch chair height right there, I'm going to really say my CGS and my tendon needs to be 5 3/4. Is that why I called out? And then come down to my low point, which is right, see, 1.5 inches right there. So that means on my drawings, my CGS that I will have been calling out will have been 2 1/4 inches, because we're going to take 1.5 inches plus a 1/2 inch number 4 bar plus half the distance to get to 2 inches plus half the distance of the 5/8 inch tendon, which gets you to 2 1/4 on there. Remember, it's 1/2 inch thick strand, your tendon strand, but then with the sheathing on there, that plastic sheathing, that adds another 1/8 inch. So it's 5/8 inch total diameter. You're not going to split hairs down to 1/16 inch. So we're just going to round it to the closest 1/4 inch. You as an engineer, I'm going to keep saying this just to drive this point home. You're going to specify your low points, your high points, and the total amount of force that you're stressing out here. You're going to let the PT supplier figure out where to put those chairs and at what height those chairs need to be to get said elevation to get you that curvature that you want on there. So here's an example of kind of what this actually looks like in the field, right? And you can see here's a number 4 bar that's running right here. And then it's sitting on top of a little plastic chair. It's really hard to see, you guys squint, but it's sitting on top of a little plastic chair right there. And then it's working its way up to a slightly bigger chair over the high point. You're starting to get the curvature. Here's the lowest point on the slab. This was a 1-inch bottom CGS. And when you have 3/4 inch clear cover at the bottom, you obviously can't do a number 4 bar down there in a chair. It's just too small. So they make these little slab chair bolster things that you can put underneath that are 3/4 inch thick, and then you're just adding that 1/4 inch to get to the middle of your tendon right there for a low point on it. Again, we talked about there's really no rebar on these slabs. You can see the rebar to support the chairs. You can see this was the parking garage, so you can see the green epoxy bar over the column head right there. But past that, there's no rebar in this slab at all anywhere else. There's a little bit behind the anchors, but very clean, quick, fast slab to install. So with there being really no rebar in the slab, one of your biggest risks is early age shrinkage. If you look at any concrete shrinkage model, the majority of your shrinkage happens within the first few days after you poured the slab. That's why curing is so important on there. The challenge with these flat slabs is they're super thin. There's a ton of surface area. There's not a lot of volume, so you're extremely susceptible to early age shrinking. You know, that kind of plastic shrinking right as you poured it, and the shrinkage within the first couple of days, and you have no rebar to mitigate any of that cracks. So you want to get these decks stressed within 3 days of, within 3 days of pouring that concrete. You want to have those decks stressed, meaning your concrete has to get to a certain PSI. Otherwise, what's going to happen, especially in these drier Rocky Mountain regions, is you're going to start to develop shrinkage cracking, because naturally that slab is going to want to shrink as the moisture comes out. Remember, it's just like your kitchen sponge that you left out over a long weekend, and it started off wet, shrunk in. Concrete's doing the same thing. The moisture's leaving, it's shrinking in, and it's going to want to form those cracks. The PT support bar in this direction does help a little bit restrain those cracks, because you do have some of that bar in there. But in this direction, there's no bar. So as the slab's trying to shrink this way and this way, it's pretty common to see cracks run parallel to your banded tendon direction, because there's no rebar in there in the first few days. It's very common for those cracks to happen. They suck up when you put the pre-compression on the slab. You don't change your calcs for it. You don't account for it in any other way. Best thing you can do is just keep debris from falling in there. So as you put the pre-compression in there, that slab regains some sort of cross section there and has that aggregate interlock. All right, so behind the PT,
Kyle.
Yep.
If you go back to the previous slide, when they're casting the concrete, are the contractor, are they really careful not to be stepping on those tendons and stuff? Or is it just like a free for all and they're stepping on everything? And then, because I've seen them place regular slabs and then they're reaching down, they're grabbing the steel and they're shaking it and they're trying to place it while it's going. Like, how careful are they that that's going to end up what it looks like after?
No, great question. So they do pay somewhat attention to it the best they can, but obviously once it's covered in concrete, you can't see where it is. So when the guys are home behind and bull floating and doing everything behind, they can't see it and they can feel it some. So these chairs are actually tied in pretty tightly. So you can step on this piece right here and not, have too many issues. There is one of the requirements per ACI, as you're pouring these, you have to have a rod buster in the slab, making sure that everything's still chaired up, checking things, kind of overseeing it. So whenever you do a slab pour, you always have at least one rod buster following along, making sure everything's good to go on there. And we've had issues where people have stepped on these tendons here and created a pretty big blowout. I'd say the issues are very, those blowouts happen 1 in every 10 million square feet or so. Okay, so behind the PT heads, you have 2 bars that you're running directly behind them. And those 2 bars, I double count them. I use them for a lot of things. One, they're my diaphragm steel. Typically, that's plenty of enough diaphragm steel. You have this thick slab or deep slab. That's plenty if you actually run your calcs on your diaphragm bending. The other, though, is they help distribute the localized forces. Remember, we're putting 33,000 pounds of force when we first stress the thing over a 2.5 inch by 5 inch little square block. The max amount of load you can put on a semi truck's about 45,000 pounds, depending on the truck, plus minus. So you're putting 3/4 of what you can put on a semi truck load into a 3.5 by 5 inch little square right there. So obviously ungodly amount of stress happening right here. These 2 bars help just kind of move that stress out a little bit on there. And then the last thing they do is, say there's ever a void behind the concrete right here, they'll catch that PT head as it goes to suck in. And that's exactly what happened. Remember those beam pictures I was showing you guys earlier and all that congestion? I said, don't do this. This is a problem. Well, this is what happened on there. There's so much congestion in that particular beam, we couldn't actually get good concrete consolidation behind it. We were stressing it, and when we got to this head right here, it blew in. Actually, we stressed this head, then we got to this head, and when we were stressing this one, the combination of the two forces, it blew in, and then this top beam bar right here was the only thing that caught it from going even further into there. So it's more of a safety thing where it can keep the head from just rocketing off into outer space. Yeah, you can see we pulled off this one tendon head, but you can see just how mangled that plastic got right there. Again, 33,000 pounds of force in a tiny area is a ton of force. If you don't have good anchorage zone areas in there, you can run into issues. So that's kind of what that you'll hear called backup bar, backer bar in there. That's what that bar will help do. And that's just a common detailing practice. You know, you show that in your typical details on it. All right, so now on to that topic, right? So we have 33,000 pounds of force coming into a very tiny little area. And you kind of have two different anchorage zones. You have concrete crushing right here, and then that force has to distribute out into the slab, right? So if you're to follow how that force kind of goes out, you could mimic it as a strut and tie model and develop this tension tie right here. And this is straight out of ACI. Or you could do an FEA model on there. You have to design for that bursting force to make sure the slab doesn't explode. And that's a real force. I've seen people forget to put in steel behind the PT heads to reinforce it, and the slab blew up right there. And the rule is if you have 5 or more tendons next to each other right here, you have to design for bursting, right? If you have less than 5, if you have 4, 3, 2, 1 tendons in there, you don't. And the theory is there's enough tensile capacity in your concrete that it can take that force on there. Again, straight out of ACI. That's what ACI tells you have to do. That bursting force, they give you approximate. They say you can approximate it, and it's about a quarter of what your pre-compression force is in there. So if it's a quarter of 33,000 pounds and all of a sudden I got 30 tendons in here, that's still a pretty unreasonable force to try and design for. What they've been able to show empirically over time, though, is if you put in one U-bar, number 3 U-bar, if it's regular banded tendons, just like this, behind the head, and you can see those U-bars. It's kind of tough to see with all the junk in here, but you can see all those U-bars behind all these heads right here. That's enough to counter it. It doesn't quite calc out if you were to actually run the calcs on it, but it is enough that's been empirically shown over years and years that your slab's not going to explode. And the code says you can put one, if it's a banded tendon group, you can put one number 3 U-bar behind it. It's going to be fine. However, if you have a beam or stacked heads or anything outside of a traditional, you need to design that force. And this gets overlooked. One of the biggest things engineers overlook. And they just assume that the PT supplier is going to design it. But the PT supplier, all they're really responsible for at the end of the day is just making sure their anchor is big enough that's not going to crush locally. They're not responsible for this. Most PT suppliers are pretty savvy, and they know a lot of engineers out there aren't that smart. And so they say, we'll go ahead and design it for you. And they'll do this calculation. Now, when you're talking about a beam that's got 30, 50, 60, 70 tendons behind it, that force, also you're looking at number 8s, number 9s, so you're trying to get in there. It's hard to develop that force. So what I've done before, and you can do this through FEA, is I've gone in, I've put this in as either a beam element or a plate element. This was for we had stacked PT tendon heads, like one on top of another here on a big podium. And we were able to push on the slab and look at what that distribution, remember we were talking about the shear lag effect before, and we're looking in plan view right now, right? So we're looking bird's eye, looking down on it. And so you can see that shear lag from this area pushing out. And then you kind of see where the concentration of those forces are going to be as it moves itself out horizontally. This is where that horizontal bar helps out, right behind the heads. But then it's also kind of nice to sometimes put a couple horizontal bars back in here to help reinforce that amount. Now, if you're to look at cross section of it, so here's where the actual PT head itself is sitting. Then you're to apply that, whatever your pre-compression force is, 33,000 pounds times 20 tenons, 30 tenons, or if you're doing bar in between every single head, you just do it times 1 tenon. And you look at that, you can see the max tension force is represented by this red thing, and it develops at distance here that is somewhere between 1/3 your slab thickness and 1/2 your slab thickness out there. And it's very critical that when you go to put those U-bars in there, that U-bar is somewhere between 1/3 and 1/2. A mistake I've seen in the field a lot is they put those bars directly behind the PT head. Well, that's not where our max force is and tension being developed, and then boom, it still blows up even though you have that steel in there.
Kyle,
What you do-
why a U-bar? Like, I mean, you're trying to carry the tension across. Is the U-bar just kind of like hooking it so that you get more?
Yeah, all we're doing here is we're just giving a development length
Okay.
on there. Feel a little more warm and fuzzy, but even then, like if you look at if you talk to all those guys who are real snobby about anchorage, they'll tell you like hooks only do so much, right?
Yeah.
And but yeah, so that's the idea. Is it's just a development length for your hook. So when you look at this, you also kind of have to figure out, when you're looking at FEA, okay, this is in PSI, but we got to convert that to a tension force, right? So that means we really need to integrate across a certain section. You kind of have to use your engineering judgment of, okay, where am I going to cut this? And then it's going to give me some fancy curve, and hopefully your software is smart enough that can integrate the area under the curve and tell you what that resultant tension force is, and that's what you're going to design that tension force for right there. That's the approach you do it. And the biggest trick when you're using any FEA program is trying to figure out, okay, we have these forces at all these nodes in whatever unit it is. How do I convert that to a resultant tension force, and what area am I going to look at in there? I typically look somewhere about this area. Sometimes I'll do a little less and I'll say, okay, say this purple region represents a force, or brown represents a force that's less than a rupture, whatever coefficient of rupture I feel like using that day. Then I might only bring it to the brown, or go from brown to brown region, or somewhere along those lines. You just kind of use your engineering judgment. There's no code information out there about this. This is where you being an engineer, using your head really comes into play on it. This is what it looks like when you don't have, when you forget that steel. It's a giant tension force tie that develops in that slab, and it goes boom, and these actually go boom. And you can see this particular one, you can see all the PT heads right here, and that tension force got developed back here and blew up right back here. You can kind of still see the concrete intact right there. So that's an example of not having that bursting steel in there and just how important it is. And it's one of the things I see missed more often than not. And again, you only need it when you have 5 tenons or more. Really, even if I see 5 tenons, I'm fine with it. It's at the banded tenon groups is where it starts to grab my attention, and behind the beams on it. All right, another topic, we're going to briefly touch this one, then we're going to dive deeper into a little bit more, but that's restraint to shortening with a PT slab. If you look on the image on the left here, this is our dream layout when it comes to lateral, right? We have redundancy in each direction. These dark walls are our shear walls. We have awesome torsional resistance, everything you could ever want from a lateral perspective, right? This is the worst layout you can possibly have when it comes to a post-tensioning layout. So when you start doing these slabs in these high seismic regions, you're always fighting, okay, which one do I want to sacrifice, my lateral or my post-tensioning? And the right answer is you kind of make them both a little pissed off. And what will happen, and this is true with any concrete slab, but for every 100 feet of unrestrained length, your concrete's going to shorten by 3/4 of an inch. And there's a bunch of different models out there to study it. That 3/4 of an inch, only 20% of that shortening has to do with post-tensioning effects. And the post-tensioning effects is going to be your P over A of your elastic shortening, right? You're putting some sort of pre-compression on there. You got some P over A, you're going to get some sort of elastic shortening. And then you're going to get a little bit of long-term creep shortening of it just being under sustained load for its lifespan. But that shortening is only about 20%. And we're going to show I drew inches there, percent. And that shortening is something you're going to have to design for and really think about on the slab. So lots of times what you'll do is you'll say, okay, we might hard tie this wall in and this wall in, leave the dowels up. But when we go to pour this wall here, if we were to hard tie this slab all the way in there and I were to go stress it, well, force is attracted to stiffness, right? I have these very rigid, stiff elements here. All my pre-compression in this direction is going to just instantly dump right into my shear walls, Now we've preloaded our shear walls. We're seeing cracks in our shear walls early on. We're also don't have that theoretical P over A that we want in our concrete slab. So not before we even start thinking about shortening, we don't even have the pre-compression we want back here because they all got dumped into our shear walls. And then long-term effects on the shortening, what's going to happen as that slab for every 100 feet of unrestrained length, so let's just say this thing was 200 feet long, it's going to try and suck in 3/4 of an inch on each direction there. We're going to start to develop these cracks that you see here and that you see here on there. So you need to come up with an idea to temporarily get that pre-compression, release that shear wall, but you want to tie that shear wall back in because you obviously need to drag your diaphragm forces into it someday. And here's an example of how you can do that. On the top of this wall, we put masonite as a slip material right there. And then there's this pilaster. This was a foundation wall coming up out from there's like 2-3 stories underground. And so this is going to become a column element up above. It's a pilaster. We put some rigid insulation around this pilaster element right there. And then what we'll do is we'll chip out that rigid insulation. Now you have a gap. Now the slab can move this way and it's unrestrained. It's not going to get shear keyed in from this column. If you didn't have this, it's great. You slip this, but you got a giant shear key right here and it's going to shear key it in. But you got the masonite right here that's going to allow it to move in this direction and also suck in this direction because it's not hard tied in there. How are we going to come back and hard tie this wall together? Well, this particular detail, what I would do is I take a piece of rebar, punch it through my edge form there, and then I come back and I pour in this curb, 60 days later after a lot of that initial shortening is done. And now I have a force transfer to get my horizontal diaphragm forces into my shear wall here. But for the initial 60 days, I freed it so I could get my pre-compression to the slab and I didn't shear key it into everything, right? So that's kind of a general consideration with lateral restraints. And it's when you're doing a post-tension design, before you even start running numbers, it's almost more of a, hey, I need to just think about, not necessarily run the numbers. The software is going to run your numbers. You need to kind of use the logic in these designs to figure out how do I make sure I'm not restrained. Here's a picture of this.
Real quick.
Yeah.
So just to reiterate, so you were saying at every 100 feet of pull length, you'll shrink 3/4 of an inch, right? You'll lose 3/4 of an inch. It'll move 3/4 of an inch, but 20% of that is from your post tensioning. Is that what you're saying?
Correct. And the rest is from shrinkage of concrete. Mostly shrinkage of concrete and temperature. Shrinkage is your biggest one. So it doesn't matter whether it's post. So on a mild slab, you're still going to see a notable amount of shrinkage. The difference with a mild slab is you have so much rebar in there that you get a bunch of micro cracks that add up to the same macro crack that you'd be seeing right here.
Okay.
Right?
Yeah, and then so it's always crazy to me how much it moves when you post tension, right? So it moves a lot when you're doing the post tensioning, and then what you're saying is that all the load will get transferred to those shear elements, your shear walls, because they're the stiffest, right? And then you get cracking around them, kind of.
Yeah. So what I've seen with shear walls happen quite a bit on towers where it wasn't done right is, let's say this is a tall shear wall, you'll start to see, say there's this is where your force is coming on every level, right? You'll start to see flexure cracks down at the lower levels like this. Yeah. From all that force. They're at a little bit of an angle just because of all the load coming down, so they're not perfectly horizontal.
Right.
But you do start to see some of those cracks if it's not done right. So, and if you're seeing cracks like that, you've definitely yielded this bar back here.
And if you have a lateral element that's more flexible, it'll just move the lateral. Like if it was like a moment frame, the top of the moment frame will just
correct. It'll move it, but you have to make sure that it can account for that much, movement in there. Right. I've seen pictures of garages where there's been some pretty big issues over that.
Yeah.
But
Cool.
again, this is the same theory. Even if you're doing a mild slab, you're still going to get, okay, you're not going to get that 20% from the post tensioning, but you're still going to get quite a bit of big lung building horizontal shortening effects, and you're going to be seeing this stuff down at your lower levels when you start doing high rise design, if you don't kind of detail and think about it.
Yeah.
So we give a lot of those first 2-3 levels out off the ground. We give a lot of attention to our detailing down at those levels to make sure that we're not, coming up with those cracks. And I got next week, I'll show some pictures of some pretty big standoffs that happened.
Yeah. Cool. Cool.
This was a picture back when I was in my contractor days, and the engineer didn't specify anything. We knew that, hey, this is going to be a shear key. I'm not sure I even really knew at that point. I'd forgotten what a shear key even was. I just knew that was bad news bears. And so we thought we were going to be super smart and put in some rigid insulation right there. And then in our headspace, it was just foam and it was going to compress. And so we were all proud of ourselves putting this rigid insulation. Came back the next day and, perfect shear key crack going right there. What we failed to realize was just what the compressive strength of rigid insulation actually is, and it's pretty damn rigid on there. So I show this picture a lot to be like, make sure you chip that foam out on there. And we had a slip detail on top of this foundation wall with these pilasters coming up, but you can see on this column itself, just the very next day, how much you can see that dark line, how much that slab's already pulled off of that column element right there. All right, so this is kind of what your finished deck's going to look like. We've seen a few pictures of it, but again, just your support steel. You got your band tendons, your uniform tendons, a little bit of top steel right there. You got your column bars projecting out for your next lift that you're going up on. There's a wall right here, so we have some continuous bars here. And then this is just electrician's conduit running through the slab, which is something that you definitely want to pay attention to, especially as you get closer to your critical punching regions. Right in there, right? So now we know generally what these slab systems even look like, right? And kind of some of the gotchas to look out for. So now we can kind of dive a little more into the stressing of the tendons themselves in the next 8 minutes. So these post-tensioning slabs, 5,000 PSI concrete is usually the concrete you're specifying. And one of the reasons for that is 5,000 PSI concrete is going to give you a better shrinkage than anything else. The other is most of your calculations are based on their square roots of your F prime C. 5K is a good mix. You want to let them stress at 3,000 PSI, not necessarily 75% of your F prime C, unless it's like a big transfer slab. So 3,000 PSI, a lot of good concrete suppliers will get you 3,000 PSI overnight, especially if you're in more urban areas and they're pretty intelligent batch plants there. You'll test that either with concrete cylinders, or you can put, it's called a maturity meter, but you put a little meter, and all it is a thermocouple thing they embed into the slab. You go out, you measure it. And what they've done over time is they've correlated its degrees Fahrenheit times hours curve versus what your concrete strength is. So your F prime C. And they've made a curve based on pretty much they cast 40 of these cylinders, they break it every hour, and they measure the temperature of the concrete. And so you can go out there and you can essentially look at what's my temperature of my concrete and the hours since it's been poured, and I got a pretty good idea of what my PSI is, so I can start stressing. And so that's pretty common on these big buildings, throw these maturity meters in there. Like I said, all they are is it's just a thermal measuring device, but it's been calibrated to some sort of graph that's been done from early testing. So when you stress these things, it's a giant hydraulic element that stresses it. You have this jack right here that's going to do all the stressing, and then this is just your hydraulic back here. And the hydraulic's got a gauge on there where when you know you have X amount of PSI hydraulic pressure, that corresponds to this thing having 33,000 pounds of force on there. And so what it's going to do is this nose piece right here, that's going to push on the end of your PT head. And so we talked about those pocket formers, you need that access to get onto. So that's going to push onto that. Your cable's going to run right up the gut. There's little teeth that grab the cable right there. And then this moves backwards here and here. pulls that tendon till 33,000 pounds. You know you're at 33,000 pounds by the calibrated gauge pressure. You release it. And when you release it, you're really just letting go of it. And when you let go of it, it's like a giant rubber band. The thing's going to try and suck in, but as it sucks in, you got those wedges that we showed you earlier, right? They're going to catch that tendon from sucking back into the slab. Now you've put that force within there. What you do is you say, okay, in theory, I have 33,000 pounds of force on this thing based on my gauge pressure that's been calibrated. However, I need to check it another way. And the way you check it the other way is those deflections that we talked about earlier. I mentioned, hey, they showed you on the shop drawings, your theoretical deflection is 7 inches or 11 inches, wherever it ends up being. And it's a very simple, it's your classic PL over AE, right? You know you're stressing at the 33,000 pounds. You know the length of your tendon. You know your cross-sectional area. You know what E is for steel. You're, real easy to figure it out. Also really easy to figure out if the shop guys made a mistake in their theoretical calculations. But you'll go and you'll measure that elongation. And how you'll do that is before you stress the tendon, you'll put a little paint mark on it. And I usually put a little board on it. I stress the tendon. And then I come back, I put that board on, and I measure my paint mark back to the board. And my theoretical elongation needs to be within plus minus 7 inches or my actual needs to be plus minus within 7 inches of what the theoretical is on there. It's a lot harder on short pulls that are less than 20 feet to get to that number, just because when those wedges do seat, you usually lose 3/8 of an inch of elongation. 3/8 of an inch of elongation on a 120-foot tendon is a much different fraction ratio percentage than 3/8 of an inch on a 20-foot tendon. And so it's really hard to get, you can be 1/8 inch off the theoretical, which could just be an error in reading the tape measure at that small, and you could say you're 30% off on there.
But Kyle, a couple questions about it. Do you jack it up to 33 and then you're going to lose some, or do you go a little beyond 33 knowing that you're going to lose some? Right?
Yep. So you jack it up to 33 knowing you're going to lose some. And 33 kips is 80% of your ultimate, which also corresponds to about 90% of yield. So there's not a lot of room between yield and rupture on it, ultimate being when it fractures, right? And so you stress to 80% of ultimate, and then when you release it, it's going to drop down to somewhere around 29 to 31 kips. So it's going to drop down to somewhere around 70%. And you're going to have losses from friction of it going up and down, friction from the horizontal sweeps. You're going to have losses from the slab now sucks in by its elastic compression. And then the seating, those wedges as they seat in, that takes 3/8 of an inch or however much, that tendon's going to suck in a little bit. So those are your initial losses that you're going to have. It's going to bring you to 70%. Then over time, we talked about all that shortening, right? That was going to happen earlier. And we said a lot of it happens right at the beginning, but you get that shortening over time. Most of it's from shrinkage, a little bit from creep. Then you're going to have all that shrinkage shortening and creep shortening. And then after all that's said and done at year, call it 5, you're going to be down somewhere around, the number you use for your calculations is 26.8 kips per tendon. And they usually come out somewhere right around there. If it's a longer tendon, it might be a little less, shorter tendon, a little more on there.
So Kyle, one more question. So is that does the supplier, are they the ones that tell you the 26.8, or is that something that you're who's estimating those losses, long-term losses? And my second question is it scary? Is it scary to stress these things?
Yeah, super scary to stress these things. I stand pretty far back. That hydraulic piece, you actually want to have it as far back away from the ram as you can. Because again, you got 33,000 pounds of potential energy on the thing. When the thing decides to go, she goes. Right. And I've seen tendons shot across a field before. But it doesn't happen that often. It's usually a result of somebody screwed up somewhere along the lines of installing it. But it does happen. And then, it's me as the engineer, I go, all right, I know it's 26.8 kips. So as I'm designing my banded tendon groups, I might have 15 tendons in there. I go 15 times 26.8. That's the kips I show on my drawings of that's how much final effective force you need in there to set them up for success, to be like, okay, you got this right number right there. It could be 26.8, this could be 27.5. It could be 25, but you're somewhere, you're within 5%, close enough. And again, it's structural engineering. Our margin of error is huge on it. So, anyways, you'll get the stressing results from the PT supplier, or actually from the inspector on the field. They'll measure against the theoreticals. They'll give you this report. They'll tell you, are you within spec, without spec? If you're not within spec, you can always relift it off. That's dangerous, and restress it. Typically, I try and justify to myself it's okay because I have a few extra tendons in there anyways. The other thing to look out is just intermediate stressing points. Here's a tower crane block out. Here's a slab. You can see the tendons coiled up to the next pour right there. This is what, I don't know, 4 feet right here. You would not stress this tendon at this intermediate joint right here because it would instantly break just trying to get up there. You don't want to stress anything less than about 20 feet. But back here, you can see where you got lots of room behind it. And this is what an intermediate anchor looks like at stressing joint. It's just the anchor that goes onto your tendon. It's a continuous tendon. You just stress it right there, and then you stress it again at the next pour there. So what we'll get into next on Friday is we're going to kind of talk about reshores, and we're going to start kind of flirting with design a little bit and starting to get into some of the concepts of design from Friday. So
Cool. Thanks, Kyle. That's awesome, man.
all righty, guys. Enjoy your Wednesday, and I'll chat with you guys Friday morning.
Awesome. Thanks, Kyle.
Yep.